My name is Amar Vakil, and I have a bachelor's degree in electronics engineering technology, and it's from Southern California Institute of Technology in Anaheim. And I have a associate's arts degree in mathematics from Irvine Valley College, and I'm pursuing a dual major in chemical engineering and applied mathematics at Cal State Long Beach. I have 20 years of experience in computational forensics. It's information theory. When you filter data, you're making an assumption for linearity, but when you're dealing with nonlinear data, you can't make any assumptions because you don't know what dimension that information resides in statistically. I'm also board certified with the California Board of Professional Engineers and Land Surveyors. When people see this, what they're seeing right away is that you have rollers turning around the stator. Whether we know exactly what's going on or not, the bottom line is something is unusual about this device. And since it's different than what we normally encounter, it's natural for anyone to ask, can this be investigated further using the scientific method? Whether it is something trivial or not is not the issue here. The issue here is that is there an explanation to it that can help us better understand how it works? We have to be responsible as individuals to make sure that our data is tainted, because if the data is tainted, it's all over. If we are not responsible as individuals to make sure that our data that we're looking at is not pure, that it is not manipulated by someone else, then we run the risk, even though we mean well, we run the risk of creating more tainted data for others. And that can become it's like a self-fulfilling prophecy. It just keeps happening. And that's what we need to be very careful. And then we go from data to information, from information to knowledge. These three books here are on nonlinear optics by Prigogine. It's Advances in Chemical Physics. The series editors are Prigogine and Stuart Rice. Prigogine, as I understand it, he was a Nobel laureate when it comes to chemical physics. These three books cover a broad range of areas involving the electromagnetic phenomena, but it has to do with not the one that's normally covered in the standard literature of physics and electricity. It seems to go past that point. It is covering areas that have to do with higher level mathematics that is normally not taught in schools. Addresses higher symmetry algebra, mathematics that would be required to better understand how this advanced electromagnetics relates to general relativity and potentially lead to a unified field theory when it could potentially encapsulate many of these patents and devices that perhaps are dealing with that kind of an area, but they're not quickly acknowledged or are not readily addressed, not readily looked at by the mainstream community because of the subject matter. You have to have a starting point somewhere to at least begin to start questioning and resolving. These are very fringe areas, and what often happens to anyone investigating them is that you're basically walking into a minefield. What intrigues me here is that when we're looking at the way the Searle device operates, we're looking at physics that we normally don't encounter. When we look at the standard physics literature taught in universities, taught in schools, we're talking about circuits that are closed circuits. Whereas Searle's technology, if you were to write it, if you were to look at it as a circuit diagram, which I personally investigated, what I find is that it's not a closed path circuit, it's an open path circuit. The rollers have impressed me from day one. The fact that you can get these rollers to pick up and turn about a stator, that alone is impressive. To me, that is different. That is something we haven't seen before, and that needs to be investigated. Some areas are extremely sacred, and I would say that the second law of thermodynamics, I have a great deal of respect for it, and I think that we all must understand what these laws mean. But at the same time, it's the responsibility of an investigator, a good investigator, to make sure that that if something does not fit what we normally observe, we need to at least take a look at it and look at it and even if the second law states that it's within, this has to be based on what should be going on. There's no harm done in to go out for just a moment and take a look and see, could there be something else going on over here? Could the second law be a subset law of a much larger set of laws? And when we talk about space-time, and that's a whole big area because there's still much to discover there as well. One thing we never account for in the second law is the transduction of mass. Mass transduction is a whole concept that is, in a way, it's almost it leads from a polite discussion to a rather, some folks would call it a dogfight, but we can't completely ignore it. Mass is all around us. How does mass get there in the first place? We always look at it from a strictly anthropocentric process from beginning to end, but how did it get there in the first place? Where is it coming from? When we look down at the subatomic level, what are we looking? We're seeing spaces, we're seeing gaps. So what does quantum mechanics have to tell us about this? We seem like we're hitting roadblocks. So there has to be something else going on, or there has to be at least room to ponder on other areas to look at, because we got abstract edges to work from, and that's not a good enough gripper. So coming back to the second law, if it is part of a subset law, if it's a subset law of something much larger, what we're talking about is as if mass is coming from 4 space, coming into 3 and then going back into 4, but we only see the part that's happening after the fact, after the collapse of the wave function. And I'll,
In 3.
In 3. So everything we observe, what we're observing is what's already happened. What we're not observing is what is happening. And if you look at it from that standpoint, past, future, and present are all here. And of course, it's really hard to go from John, to go from John Searle's device. What's really tricky about John's device and a lot of devices is that sometimes you have an object that is, you have an application that's sitting at the, some folks, I'm very careful with terminology, as I mentioned earlier, and that is, I don't use the word para, I use the word peri-normal. So it's at the edge. And when science is at the edge, it's extremely important to understand how much we already know and what we don't know. And like a good crime investigator, you got to put a yellow tape around it, and you got to know that what you don't know, you don't tamper with. You do work with what you do know, and then put a shell around the stuff that you don't know, and then label the shell with what you do know. And that way you make sure nothing goes in and nothing goes out, and you continue to investigate it at the data and information level, making sure that that data is as pure as you can keep it. And that's a tough thing to do. That's a challenge that every scientist, every engineer, every mathematician has to undertake, and it just comes with the territory.
And still, the scientists say it's impossible to do. Really? Well, we're going to show you. They're wrong.